Welcome to this module. Now, in this module we will look at the range of amplifiers. So, range of feedback amplifiers in particular. However, in the next set of modules we will be looking at several signal conditioning circuits, including how to design a voltage control oscillator, which is VCO. We will also see how to measure the ECG signal bits per minute, right, and what kind of electronic signals or circuits we can design to grab those signals and to display it final in form of PQRS waves. We will also see circuits for temperature compensation in case of thermocouple. We will also see on off controller, proportional controller and several such electronic modules, right. So, to start with, every or most of the things that I am teaching here in theory we have designed in experiments. Either the experiment is through simulations or it is shown to you as a demonstration. Particularly one experiment which is very dear to me is ECG measurement, and we will be showing you how to measure ECG taking an example in reality, in real time. So, how to place the electrodes and how to design the circuit and how to measure this. So, this is a big experiment about 2-3 hours at a later stage of this particular course. So, let us see this particular module, and like I said, this module is focused on understanding the range of feedback amplifiers. Now, what do you mean by range? So, let us see. Now, if you see this particular circuit, this circuit is unity gain amplifier. What is this circuit? It is an inverting amplifier, this one non-inverting amplifier, right. We have already studied in previous course. So, it is now very easy for understanding whether it is inverting or non-inverting or unity gain amplifier just by looking at the circuit. Now, if I talk about unity gain amplifier, what does it mean? The unity gain amplifier is amplifier which will follow the voltage, right, and increase the current. It can also be used as a buffer, right. So, the unity gain amplifier, inverting and non-inverting amplifiers are connected as shown in figure 1, 2 and 3. The gain of inverting amplifier and non-inverting amplifier is 2. Now, how is this possible? See, this is 2R, this is R, right. Here it is R and R. Still we are saying that gain of inverting and non-inverting amplifier is same, right, because we already know that the gain is nothing but VO, which is output voltage, equals to minus RF, which is feedback resistance, divided by input resistance into V in, right. This is for our inverting amplifier. If we talk about non-inverting amplifier, our output voltage is nothing but 1 plus RF by R in into V in, correct. So, if you see, then what is the gain? Gain is this gain, here gain is this one, right. So, if I say VO by V in equals to minus RF by RI, this is this equation. Now, if I substitute a value for inverting amplifier, what is RF? 2R. So, this is equal to this, if I place it, is 2R divided by R, which is 2, right. So, this we get 2. Now, if you take a case of a non-inverting amplifier, then you can see our equation is VO equals to 1 plus RF by R in into V in. So, if I say VO by V in equals to 1 plus RF by R in, this is the equation, correct. Now, if I substitute values, then 1 plus what is RF? R. In this particular circuit, what is RF? R. What is R in? R. So, R gone, that is 1 plus 1, this is equal to 2. So, here also we have 2, right. Thus, the gain of inverting and non-inverting amplifier for the circuit shown are same, or the gain is same. Now, the maximum input frequency at which the output voltage reaches to its saturation is to be observed. So, at what input frequency the output voltage reaches to its saturation? Let us see. If you want to do that, we have to perform an experiment, right. So, the procedure for finding the range of the feedback amplifier is connect the circuits as shown in figure 1, 2, 3, which is right over here 1, 2 and 3, right, and then apply a sine wave 1 volt amplitude and observe the generated output voltage in the oscilloscope. That means, I will apply a sine wave 1 volt amplitude 1 volt peak to peak amp voltage, right, and I observe the output voltage in oscilloscope. In every case I will apply 1 volt here, here and here, and at the output I will see what is my value in my digital oscilloscope. Okay. Then change the input frequency and measure the amplitudes of input and output voltages. If I change my frequency here, right, I need to measure what is the change in my input and output voltage, that is the third step. So, if you see here, what we will do? We will write input frequency, then we write input voltage, we measure output voltage, we change the frequency and we see input and output voltages. We need to understand at what frequency our output voltage reaches its saturation value, right, which is its saturation value. This is the experiment. This is the experiment that we will perform to find the range of feedback amplifiers. Alright. So, it is very easy, you can take an operational amplifier, right, give the bias and start working on this particular experiments. Now, to do that, the things that we have seen particularly about circuit designing, my TA Sitaram and Anil, they will discuss about how the circuit operates. We have seen in theory in detail, but we just need to have a quick recall of how circuit operates. So, they will show you about that circuit operation. I will request Anil to join us and show us how the experiment procedure can be carried out, and these experiments I feel that if you learn, it will be good for lot of other applications.
So, we have seen the theory section where we saw what is the range of an op amp circuit which is connected in negative feedback as an amplifier. So, what do you mean, just a quick recap, what do we mean by the range is that. So, as we know, the op amp has a saturation voltage which is around 13 volt, 13.5 volt, when the supply voltage is around 15 volt. So, because the op amp has a gain, when we give an input, we get the output that is multiplied by the gain, which this gain here is the closed loop gain. Okay. So, what is the range of the op amp? As we have studied just now, the range of the op amp is the range of input voltages that give corresponding output voltages without saturation. That is the, in a practical term, that is the range of an op amp based amplifier circuit. So, as you can see, that range is very much dependent on the kind of gain that we have provided for the circuit. So, today in this experiment, what we will do is we have connected an op amp in its inverting configuration, and we have given a gain of 2.2, roughly 2.2, 2.5. So, the gain, as you know, is constructed by a resistor combinations. The gain of an inverting op amp is given by minus R2 by R1, where R2 is the feedback resistor from the output to the input. The input here is the negative terminal of the op amp, and R1 is the input resistance, after which we give the input, correct. So, that the formula for the gain is minus R2 by R1. So we have to select resistors. The resistors will have their tolerances. So, what we have selected here is 2.2 K resistor and 1 K resistor as R2 and R1, and we have connected it up, but because of the small resistive fluctuations, we will get reasonably similar gain. So, what is the gain? Theoretically would be 2.2. We will see practically what is the gain we are getting, and more importantly, we will see what is the range of input that is giving an output that is not saturated. By telling that the output is not saturated is that the output does not get clipped off at the saturation voltages of around 13.5 volt. So, let us quickly see how we have connected the circuit in the board. So, here as you are aware, we have connected the circuit in the op amp section of the analog circuit development board. So, we have used the basic type 3 op amp section. We have connected it in the inverting configuration. So, the input, this pink wire, okay. So, if you can see this yellow wire, you can see that the probe is connected. So, the input comes from this probe, okay, and it goes through a resistor on this breadboard, you can see, and so it is there here, and then this pink wire goes to the inverting terminal of the op amp here, okay, and then the positive terminal of the op amp is grounded because it is a inverting op amp, and the output is connected across a resistor here back to the board, back to the input, okay, and we see the output from the output terminal. So, how do we see the output? The output is seen from the output terminal using this probe, okay. This is a very simple circuit, but the understanding that you get from this connection is very profound, which can help you in further building of more complicated analog circuits. So, this is how the circuit is connected. So, now let us check the how the circuit is working. For that, let us see the function generator to see what is the input that we are applying. So, let us see the function generator. So, this is the function generator from which we are applying the input. As you will be able to see, we are giving 10 kilohertz sinusoidal input voltage, and the input voltage that we are starting off with is 1.5 volt, 1.5 volt peak to peak voltage. So, that is like the single excursion, one side excursion will be around 0.75 volt. So, we are giving 1.5 volt peak to peak. So, what is the gain of our op amp? The gain of the op amp we have given is around 2.2 volt. So, 1.5 into 2.2, it will be around 3.5 volt. It is not exactly, we have to multiply and see, but it will be above 3 because 1.5 into 2 is 3. So, 1.5 into 2.2, it is around 3.5 volt peak to peak should be your output, clear. So, this is the input. Now, next what we will do is, we will not see the function generator again. In the function generator, by changing the input with this knob, we can increase the voltage. So, this way I will be increasing the input voltage from 1.5 volt to 2.5, 3.5, 4.5, 5.5 etc., and we will see at what voltage we are seeing clipping action taking place in the output. By clipping action, meaning the output is getting saturated. So, we will constantly change the input and see how the output is changing. When I am changing the input here, I will tell which voltage is being fed through the function generator, but we will focus. We have seen the circuit, how the circuit is connected, and we have seen that the oscillator is connected to the output terminal. So, now henceforth for this experiment, we will focus on the oscilloscope and see the output on the oscilloscope, and I will accordingly tell what is the input that we are giving from the function generator. So, now let us see the oscilloscope. Yes, so we can see the oscilloscope. So, as you can see, this is the output from the output terminal. If you remember, we have given 1.5 volt peak to peak for the input. So, if you see the output here is 3.2 volt here, 3.2 volt peak to 3.23 volt peak to peak. So, this is aligning with our gain formula, which is 2.2 is the gain. So, 2.2 into 1.5, it gives you around 3.2 volt. So, this is like we are getting almost with 95% accuracy, we are getting the output. So, this is the output voltage. Now, let us change the input. So, I am going to change it, the input in steps of 1 volt. So, from 1.5 volt, I am changing it to 2.5 volt. Okay. So, let us do an auto scale so that we can see the whole signal. So, we can see the whole signal. So, now the output voltage is 5.32 volt, which is again matching, correct. So, 2.5 volt. Now, again I am increasing it to 3.5 volt. Okay. 3.5 for 3.5 volt, what is the output? We are getting 7.4 volt, again matching with the 2.2 gain formula. Again we are making it 4.5 volt. So, 4.5 for 4.5 volt, we are still getting a beautiful sinusoidal wave without much noise in it, with the peak to peak output voltage of 9.68 volt. Okay. Now, we are increasing it again, now it is 5.5 volt. Okay. So, like that now the output voltage is 11.7 volt. So, let me keep increasing it. So, this is 6.5, 7.5. Okay. So, as per formula, so we know that the saturation voltage of the op amp is when supply voltage is 15 volt, is around 13 to 13.5 volt. So, that 13.5 volt will be the single phase single side excursion. So, positive side should be 13.5 volt, negative side should be 13.5 volt. When that voltage is reached, the output saturates, correct. So, with a gain of 2.2, let us first try to calculate what is the input voltage for which the saturation will begin to occur. So, as per that, so 2.2 is the gain. So, around 13 volt. 13 volt is a single side excursion, correct. So, 13 volt single side excursion means 26 volt peak to peak, correct. So, 26 volt peak to peak by 2.2 will give you the input voltage for which saturation will start to occur, which is what 26 by 2.2 is around, is less than 13 volt but more than 12.5 volt. So, around 12.5 volt input you should begin to see the saturation. So, if when you begin to see the saturation, the input voltage will be 12.5 volt peak to peak. So, then we started from 0 volt till 12.5 volt peak to peak, then the point where saturation begins, and from the input start value 0 to 12.5 volt peak to peak or 0 to 6.25 volt sinusoidal wave would be the range of the operational amplifier, correct. So, let me increase the input again. So, now it is 8.5, now it is 9.5, 10.5, 11.5, okay. So, next it will be 12.5. So, it is 12.5. Now, let me increase it in more fine duration, so that you will see when the clipping starts to happen. So, now it is 12.5, I am making it 12.6. So, if you properly see it, okay, you can begin to see a slight clipping happening here, okay. So, let me increase it further, okay, 12.8, okay. Now, you are seeing very nicely, you are seeing the clipping action, right. Now, it is around 13 volt, okay. So, 13 volt peak to peak. So, that is around 6.5 volt input voltage, you are getting the clipping action. Now, the peak to peak voltage here is 26.4 volt, okay. So, you are seeing the clipping clearly. If I increase it further, you can see that the saturation effect becomes more profound and more expressed, correct. So, now you can see that the output has become clipped, it has become, it is trying to become like a triangular wave. So, this is not the desired output as per design. So, what is from this experiment, what you can see, the range of the op amp is from 0 to around 12.5 to 13 volt peak to peak input, or 0 to 6 to 6.5 volt peak sinusoidal wave is the range of the op amp. By range of the op amp we mean the input range, input signal range. Now, from this experiment it is very clear to you that the range of the op amp is determined by the gain that is given on the op amp, correct. So, then for us to get maximum range, what should be the gain? The gain should be unity, correct. So, so we will see now what is the operational amplifier with unity gain. It is called the voltage follower circuit or the unity feedback circuit. For the voltage follower or the unity feedback circuit, we will get the input range maximum, okay. So, the output will follow the input. So, we will see next that circuit, and then we will understand the importance of the gain that we apply on the output, okay, sure. So, let us just see that. So, we have just now seen the op amp as an inverting amplifier, connected as an inverting amplifier with a gain of 2.2. We have seen how the output is varying with the input, and how what is the input range, correct. So, now best circuit to demonstrate the effect of gain and the range of an amplifier is the voltage follower circuit. So, we have connected the voltage follower circuit in the board. So, what is a voltage follower circuit? Voltage follower circuit is an op amp circuit that has unity gain. So, it is also called the unity gain amplifier. So, for that we need to use the op amp in its non-inverting configuration. Why? Because what we do in the circuit design point of view is we connect the output back to the input. So, we connect the output back to the, we need negative feedback, right. If it is positive feedback, the output will simply saturate or oscillate. So, we convert the output back to the inverting input terminal, okay. So, what is your R2 resistance then? Then your R2 resistance is 0. R1 resistance you can even give an input resistance, because that does not have an effect, because the gain. So if you use the inverting amplifier only as the circuit for voltage follower, your gain relationship will be what? Minus R2 by R1, right, but your R2 is 0. So, your gain will be 0. So, that is why we use the non-inverting configuration. So, for the non-inverting configuration, the gain is 1 plus R2 by R1. Here your R2, because you are connecting from the output back to the input, is 0. So, 1 plus R2 by R1 gives you effectively 1 plus 0. So, the gain is 0, the gain is 1. So, you get a gain of 1, and we are connecting it in a non-inverting configuration. So, that is the overall idea of how the circuit is designed. It is a very simple circuit, but it has a lot of applications. The unity follower or the buffer amplifier, it can be called, you can call it, or the voltage follower. The thing is that it gives a good, it acts as a good impedance stage, and also helps you to invert your output. So, let us say you use the inverting amplifier stage to get the output, and you want to have a output which is having the same phase relationship with respect to your input. So, you add another unity follower after that inverting amplifier block. So, you get the output in phase with the input. If you just use the inverting amplifier, your output will be out of phase because the gain is -1, correct. So, that is the overall idea. That is not related to what we are doing today, we just ventured into that. So, today we are seeing the range of the amplifier, and we have already seen the range when the gain is 2.2. So, now let us see what will happen now. So, we have connected, it is very simple connection, not much. See, so this red wire connects from the output to the negative terminal, input terminal. This pink wire connects the input to the non-inverting terminal of the op amp, and the input is given through this yellow wire from the function generator. That is all, that is the circuit. So, let us see the function generator now. Okay, so we are seeing the function generator. We are applying a frequency of 10 kilohertz. So, we are starting off like the previous experiment. We will start off with a voltage of 1.5 volt. So, we are giving 1.5 volt peak to peak. So, now what we will do is just like the previous experiment, we will see the output waveform, see what is the voltage level for that, and we will not see the function generator. I will keep increasing the input voltage, and we will see what is the output voltage and where it is saturating. Thereby, we will calculate what is the range of this configuration and compare it against the range that we saw last time. If you remember, the range we saw in the previous experiment is that the sinusoidal wave of around 12.5 to 13 volt peak to peak or 6.5 volt peak sine wave was causing saturation. So, the input voltage range was 0 to 6.5 to 7 volt, 0 to 6.5, 6 to 6.5 volt, that is all. So, now let us see the oscilloscope. Yeah, so we are seeing the oscilloscope now. What was our input voltage? Our input voltage range is 1.5 volt peak to peak, and we are getting an output voltage of around 1.68 volt. So, it is almost unity gain. So, these minor fluctuations will be there because of internal and input resistances, the non-infinite, non-ideal characteristics. So, 1.7, 1.68 volt is the input voltage, correct. So, now let me increase the input voltage. So, I have increased it by 1 volt, 2.5 volt. So, let us see, so the output voltage is around 2.8 volt. So, it is almost unity gain. So, let us keep on increasing the input. So, if you see, it is like following the input with same phase also. So, that is why it is called voltage follower, correct. So, now it is 5.5 volt peak to peak, we are getting 5.7 volt, 6.5 volt, 7.5 volt, 8.5 volt. You can see here how the voltage is changing, 9.5 volt, 10.5 volt, 11.5 volt. See that it is still not saturating, correct. I am just giving auto scale so that you can see the waveform properly. Now it is 13.5 volt, still see earlier with 13.5 volt itself we were seeing saturation at the output. Now we do not see that, because what? Because the gain is unity, you have more range at your input. Okay. Now it is 14.5 volt, still this output waveform is beautifully sinusoidal without any saturation. 15.5 volt, 16.5 volt, 16.5 volt, you are getting 17.4 volt. So, almost unity gain, correct. See, it is following nicely. So, this is the maximum that the function generator can provide. So, we have given almost 20 volt peak to peak input, and we are getting 20.4 volt output. Okay. Still the output is faithfully reproduced, input is faithfully reproduced. So, the range will go on if you are able to supply more voltages. So, when does the op amp saturate? When its single excursion goes to 13.4 volt, or the peak to peak voltage goes to around 26 or 27 volt. So, when we give around 26 volt input, we will get 26.4 to 27 volt output. So, the range of the op amp will be 0 to 26 volt peak to peak input, where in the earlier case this range was 0 to 12.5 to 13 volt peak to peak input voltage. So, thus this range was reduced because of the increased gain. So, but in a lot of applications we need the gain, correct. We need to amplify our signal. Suppose it is a very feeble mic input, we will need to amplify the signal. So, amplification is necessary. So, this is the trade off, this is how circuit design will happen. So, that is a trade off. For a increased gain you have to sacrifice your input voltage range. So, that is why range of an amplifier is an important concept to understand, and this is something that you need to inculcate or absorb within yourself before you delve into more complicated circuit design. So, one part we have seen as an experiment where we change the amplitude of the input and for different gains, and seen at what amplitude the output starts getting affected or clipped off. So, that is one part, one story about the range of an amplifier. Another aspect of range of amplifier which the professor has discussed in the class is about the input frequency. You might have seen the experiment 1 description, where we are seeing the change, we are changing input frequency and seeing how the input and output voltages are changing, correct. So this is related to what is called gain bandwidth product. Okay. So the gain and bandwidth product of an feedback amplifier circuit remains a constant. So if you have a higher gain, the bandwidth that you get will come down. Accordingly, if you have a lower gain, the bandwidth you can get is higher. So that is the overall idea, which is what in the theory class we try to see, and which is what professor has tried to explain it to you. So now, so this is another part of our the first experiment itself, which we are continuing. In the first part, just now we saw how by changing input voltage for a fixed gain, how the output voltage was changing, and for what input voltage was the output voltage getting distorted. Now what we will do is, we will repeat the same experiment. So what we did in the previous experiment, we used one inverting operational amplifier configuration with a gain of 2.2, and we saw how and the input and output voltages were related. So we are using the same circuit because we are just recording, so we are just capturing that same experiment. So what we are doing is, same inverting amplifier circuit is there. Now what the input, how we feed the input only we will change this time. So circuit connection remains the same as we discussed just now. So what we will do now is, we will keep the input voltage constant at 7.5 volt peak to peak, okay, but we will change the input frequency and see till what frequency we are getting faithful output. By faithful output, what we mean is, say we have made the gain as 2.2, correct. For 7.5 volt peak to peak, we should get around 15 to 17 volt peak to peak as the output, which is the faithful output with respect to the gain. So till what frequency are we getting this faithful output gain, okay, and from what frequency is it going down? That is what we will see now in this experiment, and we will see the same thing for a unity feed or unity gain amplifier also, where the gain is lesser, correct. So accordingly, we should observe that the output remains faithful to the input for much longer, much higher frequencies. So this is how, that is how the range of frequencies, this is also an aspect of range of feedback amplifier. Here what is the range? Here the range is the range of input frequencies which we can apply. In the first part of the experiment, what did we see? We saw the range of input voltages that we can apply. Now let us just quickly see the function generator. We are applying sinusoidal wave at 7.5 volt peak to peak and at 10 kilohertz. Okay. Now this is what we are applying. Okay. Now we will not see the function generator like last time. We will only focus on the oscilloscope, and what I will do is, I will change the, I will just show it to you here. I will keep changing the frequency, say like by 100 kilohertz. So this is 10 kilohertz, 100 kilohertz, 210 kilohertz. Okay. I will just keep changing it and we will see the output. So for 7.5 volt peak to peak, we should get around 16 volt peak to peak because the gain is 2.2. Okay. So we will see till what frequency this 16 volt peak to peak output we are getting. Okay. Now we can see the oscilloscope. Now our input frequency is 10 kilohertz. Okay. And we can see the output voltage. See here, it's around 16.4. So this is a faithful output as per our criterion. So now I am changing the frequency. Just constantly observe the output voltage. Now this is 110 kilohertz. So still it is 16.2 volt. Now it's 210 kilohertz, 310 kilohertz, okay, 410 kilohertz, 510 kilohertz. As you can see, the output voltage is coming down. So the actual, so you can maybe see till around Vm by root 2. You can put a threshold value till where you want to consider that this output is good enough for your applications. Finally, it's about your own choices, like the further what are the further circuits to which you want to connect the circuit. Let's say your ideal output is 16 volt, but you are okay with working till around 13 volt. You can go on till more frequencies. Okay. So I am increasing the frequency. So you can see that at 610 kilohertz itself, the output has become, instead of 16 volt, we are getting 11 volt, which is less, correct. So if you keep increasing the voltage, it is again and again coming down amplitude, correct. Now it's 8.2, now it's 7.8, 8 volt. Frequency is 1 megahertz now, okay, and it has become very low, correct. So we can see that if you put a very hard constraint, then you are getting the 16 volt peak to peak output, okay, only till around 300 to 400 kilohertz, maximum around 400 kilohertz. Even at 500 kilohertz, you are getting only 13 volt peak to peak, which is what we are seeing here. So you understood, right? So our gain is 2.2. Okay. For that gain we are getting faithful output only to till around 300 to 400 megahertz depending on the threshold or constraint that you keep. 300 to 400 kilohertz is what we are seeing, okay, depending on the constraint we are keeping. 300 to 400 kilohertz, by then after that it is coming down, correct, with our gain of 2.2. Now what we will see the other circuit. We will connect the input to the unity feedback amplifier, okay, and then see. So let us connect it. Just keep looking at the oscilloscope. Okay, let me just switch off the input for now, because we are going to connect it. So whenever you are changing circuits or connecting it, you have to switch off your supply, everything, and then give. So now right now we are in the board, we are connecting the other circuit, okay. So we have connecting it. Now let's just 1 second. Okay. Now so now we have connected the unity feedback circuit now. So now the gain is 1 instead of 2.2, okay. Now let us see till what frequency we are getting faithful output. Now here the gain is 1. So what is our faithful output? Our faithful output is, suppose we are giving, again we are let us look at the function generator once quickly. So this is a function generator. So again we are giving the same 7.5 volt peak to peak output. Now we will start off with 10 kilohertz, okay. Now for this circuit, what is the faithful output? Our gain is 1. So faithful output is an output that is around 6.5 to 8 volt, okay, or maybe depending on your constraints, if you want to go down, let us say around 6 volt, that is also fine. So till then, so till what frequency are you getting this faithful output voltage is what we have to see. So now so the circuit connections, everything remains same in the sense for unity feedback, just like our previous experiment. Now let us look at the oscilloscope, okay. So you are seeing the oscilloscope. So we have got 8.2 volt peak to peak output, and we have for an input of 7.5 volt peak to peak, which is correct, because our unity gain is around 1.1, 1.2. There will be some non-idealities, but this is fairly accurate. Now let me increase the frequency. Now it is 10 kilohertz, it will become 100 kilohertz, 200 kilohertz, okay. You can see that output is still constant at 8 volt, okay, still constant at 8 volt. Now it is 210 kilohertz, 310 kilohertz, 410 kilohertz. Still you can see that output is 8.0 volt. For same, for the other circuit at 400 kilohertz, we saw the output coming down considerably. From 16 volt peak to peak, it had come down to 12 volt peak to peak, correct. But here it is remaining constant. You see the difference. It's 510 kilohertz, still it is remaining constant. See, it's 8.2 volt. 610 kilohertz, still constant. 710 kilohertz, still constant. 810 kilohertz, constant. 910 kilohertz, constant. 1 megahertz, constant. 1.1 megahertz. Now it is slightly decreasing. Now it will slowly decrease. So see, what was this? Our gain ratio. Let us say now let us compare both the circuits. Now what we got, around 1 megahertz, around 1.2 megahertz, okay, 1 or 1.2 megahertz, we are seeing the output getting attenuated or distorted. Now our first circuit had a gain of 2.2, our second circuit had a gain of 1. So what is the gain ratio between the two circuits? It is around 2.2. Accordingly, our first circuit had a frequency range of around 400 to 500 kilohertz. Our second circuit is having a gain a range of around 1.1 to 1.2 megahertz. So you can see it very clearly, right. For a 2.2 gain, we have a range of 500 kilohertz. The product is around 500 into 2.2, correct. It is around 1100. For the second circuit gain is 1 and the range of frequency is 1.1 megahertz or 1100. Again the product is what, 1.1 or 1100 kilohertz into 1 or 1100. There also 500 into 2.2, 1100. So you can see that the gain bandwidth product is remaining same, and the both aspects, the gain and the frequency, will affect the range of the op amp. Here by range we mean both the range of input voltages that you can apply for a given gain, and also the range of input frequencies you can apply until when you can get your faithful output. So this completes the experimental section of understanding the range of feedback amplifier. Thank you.